To start, I would like to welcome everyone to the Warren Lecture Series. It is my pleasure to introduce our speaker today, Professor Gabriele Tebaldi, University of Parma, Associate Professor and Adjunct Professor at University of Florida. Gabriele is a very good colleague and friend. His international experience started, believe it or not, 14 years ago in January 2000 in the Department of Civil Engineering at University of Minnesota. It was a brutal winter, my first winter here. And as a result, he decided to be an adjunct professor at University of Florida, where he spends winter months. Congratulations, Gabriele. Apart from that, Gabriele has an incredible CV, in spite of just being an associate professor, which in Italy, well, I don't want to comment about that, but he is president of International Society of Asphalt Pavements, member of the board of directors of AAPT, this very important asphalt paving association, where also he's one of two people who won 2 paper awards. Quite impressive. I've never won a paper award in that AAPT. Many committees, European committees, and in United States, many publications. Also associate editor for the International Pavement of Road Materials and Pavement Design. So quite impressive activity for Gabriele. And we managed to get him to the department again here. And this time he's going to talk about crack propagation and fracture energy, some work that was done at the University of Parma, at University of Florida. And with this, please welcome Professor Gabriele Tebaldi.
Yeah, let me start from what thank you, very thank you. I remember coming here, I was remembering myself 14 years ago, young, with a terrible English at the limit of the capability to be understood. And yeah, it's not bad, it's not a good English anymore, but I try to survive a little bit better. But it was a long journey from that day, and yeah, I have really to thank you for the chance that you gave me to start my international career. And yeah, it was always a piece of my heart. It's not, but I would like to start to thanking you. Okay, let me acknowledge all the people that was involved in this series of projects that was based on the application of the HMA Fracture Mechanics theory developed at the University of Florida to understand crack initiation and crack propagation in asphalt mixture. First of all, the 2 persons that was behind the theory, that is Professor Reinaldo Roque and Professor Björn Birgisson, that is another piece of the connection in this small village that is the world. I met Björn in Florida, but I know that he came from here. Dr. Elena Romeo, my former PhD student that spent a lot of his time working on that. Professor Riccardo Roncella, that is the person behind the DIC method that we developed. Dr. Jian Zhu, Dr. Marco Isola, and my master student Simone Musetti that was involved in several steps in this long work. So, where the problem starts? The problem starts from one of the most important distress and damage that you can see every day in every part of the world in the road that take you from home to the office, that are cracking. Those are the typical evident part of a distress that involve the low temperature behavior of asphalt mixture. Now, today, I will talk about the basic concept of the HMA Fracture Mechanics that was a theory and a theoretical approach defined by Roque and Sankar almost 20 years ago, and the work that we did to define the fracture energy characteristic from the experimental point of view and in different parts of the material, and what is the role of the filler. Filler is one of the part of the component of the skeleton of the aggregate part that compose the HMA, the mixture. So let's start with a background of HMA fracture mechanics. The basic principle of this theory is that the assumption that in the asphalt mixtures, creep is a damage, is a way to dissipate energy and make damage in the material. And the second basic principle is that a damage threshold exists. What it means? It means that if the stray energy stay below the energy threshold, no failure happens in the material. So micro crack develop, but due to the property of the healing that the material has, that is something that is not still very well defined. It is a property due to the thermal susceptibility of the bitumen that allow the material to close and to diffuse in the micro crack and realize a real healing effect. So if we are in the basic concept, if you are below the energy threshold, the healing is able to seal the micro crack. If the stray energy go up of the energy threshold, the healing is not able to heal the cracking, and we have damage. So not healable macro crack. So following this approach, we can define the micro crack when we are below the threshold and the macro crack when we are up of the threshold. We can see not visible and visible from another point of view. So following this approach, we can define two different thresholds. One named dissipate creep strain energy and one that is the total fracture energy. Dissipate creep strain energy is the energy dissipated by the creep of the material. So you apply load, the material starts to dissipate energy, and if the micro crack make some kind of coalescence and go up, you have the first crack that appear in the material. If the energy is below, you have nothing, and the micro crack can be healed. But if you have one pass, one load that involve the elastic part of the behavior of the material, you can go up in the over the other threshold, and again you can have a not healable crack. But if you stay below the dissipate creep strain energy and below the total fracture energy, you have no cracking that appears. So you have some micro crack, but the healing property of the material can, let's say, seal or let's say repair the material. So what we can do, that is in the normal days, in the normal service life of the pavement, we have the potential of, for this, in one day you have damage that appear, but if you are below, if the pavement is correctly designed and the strain energy is not too much, when the car and the load is not applied, the material has the time to be healed. So we have healing, and the material start again and again and again. So if we are doing the right job in the design phase, we can keep the damage below the critical threshold. So we can define, following what I just explained, the total fracture energy as the combination of the creep plus the elastic part of the energy, something like the area below the stress and strain curve, considering the stress and strain curve until the first fracture. So when the first fracture appears, means that in that area of the material, the threshold was overcome. And from the fracture energy, if using the elastic property, resilient modulus could be a way to estimate the elastic property, or some other prediction. So in some kind of way, if you are able to have an estimation of the elastic property, we can take out the elastic component in the stress and strain curve, and we can define the dissipate creep strain energy as this area. As was designed, everything was calculated following the superpave IDT procedure that is based on the IDT test and in a series of 3 different tests carried out on the same specimen, applying load and measuring vertical and horizontal deformation. We have the resilient modulus with cyclic load application, the creep with static constant load with time, and after that the strength increasing the load until the failure in a strain control test. Again, looking in the traditional approach of the crack propagation, that is the Paris law, we can have an interpretation of this phenomena from the point of view of the HMA fracture mechanics, considering a propagation step by step in the material. So if you have your material and somewhere in the material location the threshold is reached, you have the macro crack initiation. Again, from there starts some micro crack, and as soon we reach the different threshold, we have a coalescence of the crack that develop the crack in the material. The last topic, how was possible to define the point where the first crack appeared? At that time, the DIC method was still not developed, and at UF they defined a way to identify the point of the first crack using this definition of deformation differential, that is a difference between vertical and horizontal deformation, and the peak of this curve is considered the point where the first crack appears. That is before the peak of the stress and strain curve, because the material is considered failed when the first crack appears. Now let me go in the part where I was most involved, that are the definition of the different characteristics of the fracture energy. So, what I call characteristic of the fracture energy is that we were able to verify that the fracture energy defined following the HMA fracture mechanics is constant in the material. So we were able to calculate, thanks to the DIC approach, at the fracture energy in the different point where the crack started, and we had the same level of the fracture energy in the different point of the material. We were able to show that this approach was independent from the specimen geometry and not affected by the polymer modification. For who is not in the field of the asphalt pavement, you know that the bitumen, the black part of the asphalt, could be natural bitumen or could be the so-called polymer modified bitumen. So it is a technique that allows to add polymer inside of the bitumen to improve the elastic behavior of the material and also the strength of the material. So the hypothesis was that changing the internal property of the binder was possible to have a change in the general behavior of the material, and maybe the approach can be identified and the basic hypothesis must be adapted at this internal change of the material. We were able to show that the hypothesis was still valid even with the change in the fundamental property of the material. And for that, we measured the fracture energy density from multiple test configuration in both cases of material, unmodified and heavily polymer modified bitumen. So with different amount of polymer inside of the bitumen, and so different mechanical behavior of the material. The 3 test configuration used in the following part was the traditional superpave IDT test, the semicircular bending test that is quite popular here at University of Minnesota, and the traditional 3-point bending test. Considering the property of the bitumen that is strongly sensible to the strongly affected to the change to the temperature, for the bitumen that we used in the material, the HMA was the same aggregate, same bitumen, same structure in all the conditions, same bitumen except then the amount of polymer inside of the bitumen. We followed that the hypothesis of HMA fracture mechanics in that case was reached at 10C. 10C is the specific case for this material. Otherwise, you have to check if the property of the HMA fracture mechanics are in agreement or not with the characteristic of the bitumen and change the temperature of your test. And the load in all the tests was monotonically applied at the same constant stroke that was 0.084 millimeter per second. The first, this was the information about the material. Same aggregate type gradation, limestone, calcareous sand with 12.5 millimeter nominal maximum size to define the aggregate size, and 3 different asphalt binder, 2 different unmodified bitumen, and different SBS and a 6.5% SBS linear polymer modified bitumen, using as a base one of the 2 unmodified bitumen. Why 2 unmodified, the so-called natural? Because the bitumen are strongly dependent from the crude oil that is the origin of the bitumen. Probably you never consider that the bitumen is the big recycling operation in the world, because to produce the gasoline, the residual part of the refinery plant is the bitumen. So, to be more flexible in the evaluation was necessary to go forward respect the traditional technique to use it to measure vertical and horizontal strain. There is, the limitation of the strain gauge or the clip gauge is that they don't provide a pointwise analysis. So it's defined from the beginning where you are taking your measurement. And do not provide it's not possible to be flexible. So if something happened where you measure, you are lucky. Otherwise, you have to do the test another time in another hypothesis. And so it's not possible some kind of back analysis. So identify the critical point and do all your calculation in that specific critical point. And was difficult, and is difficult with that technique, to have a full field displacement strain measurement in the specimen. So we have something local, just related to the point where the clip gauge are fixed. For that purpose was specifically developed a DIC method based on grayscale analysis. So the basic concept is that one pixel with one specific level of grayscale, if the area, the so-called area of interest, is sufficiently small, if we found the same grayscale in 2 pictures, and if the area is small, we can make the hypothesis that it's the same pixel that changed the position. Of course, more you increase the area, more the probability to find similar grayscale is higher, and the accuracy of your measurement go down. The system was very simple, was based on a digital camera with a couple of lights in order to take out any kind of shadow, and at the time was not so easy to find cold light, because the risk is to increase the temperature of the surface and make some kind of alteration of the real property of the material. And to have the right contrast, in this case was used a soft white water paint, and some random black dot in order to maximize the contrast in terms of the grayscale. If you have other material, not black like the asphalt, maybe you can do without this particular technique. Now it's simple, but I have to tell you a secret, that at the very beginning we spent some months measuring the fracture energy of the paint, because we was too much concerned to the fact that the paint has to be completely attached to the material, that we were not considering the strength of the paint. And so we spent a lot of time with strange results, and we realized that at the end it was the fracture energy of the paint. But this was something that happened. So first step was to verify the hypothesis that the HMA fracture mechanics, the fracture energy in agreement with HMA fracture mechanics, is constant in the material. For that purpose was fundamental to have the DIC, because we took the picture of the specimen during the test, and we made the calculation of the stress and strain curve and the fracture energy in the point where we know that the crack will appear. Because we know where the crack appears, coming back in the picture, we can identify the point and make all the calculation. For that purpose was used two different test setups, the IDT test setup and the semicircular bending beam test setup. Again, same condition that I showed before. The stress analysis was, the strain analysis was made using the strain gauge in the back of the specimen and the DIC in the front. Was necessary at that time to have two different measurement techniques. In particular, this one was used as a proof that the DIC method was giving us the right strain field, because we were at the very beginning. I'm talking about, I think that was 2005. At that time was not common the use of the DIC, so a lot of people was concerned about the real capability of that method to give us the strain field. So as you can see, the strain curve, of course, is more clear and more well-defined, but at the end of the story, considering some noise due to the vibration during the test, we are more or less in agreement with what's happening in the front and in the back of the specimen. And this was the very, very preliminary way to make the crack path. At that point, we used manually make the dot in the material. And the process was starting, identify the crack, coming back, and we calculate in different points in material and in the different test configuration the fracture energy, and we found a very good agreement with the fracture energy calculated in the different point. So, using that result, we were able that is a constant of the material, independent from the location of the crack and from the stress distribution behind the crack initiation. Second step is to verify that fracture energy is independent by the specimen geometry, so independent by the stress field behind the crack initiation, and that was not affected by this big change in the mechanical performance of the material, because bitumen is a material with is a viscoelastic material, but adding polymer, we increase a lot the elastic part, so we are changing the mechanical behavior. So was not so clear that the change was not affecting the hypothesis of the HMA fracture mechanics. And the other hypothesis that can be used to predict the crack initiation. Again, we do the test in different configuration for both kind of bitumen, and here I will show you some of the result. Again, double way, the string gauge in the back and DIC in the front, and we found quite nice correlation in terms of first crack of course, was not in agreement because we are looking in the both side, was not a three-dimensional, no, is not a three-dimensional analysis, and something that can happen in one phase is not exactly at the same time in the other, but considering that the thickness of the specimen is 5 centimeters, it's possible to assume that more or less the time difference not make a big change. So what's happening in one phase follow closely what's happening in the other one. And so we made an analysis on the test. Here is what's happened with the this is the superpave IDT. Those are the results using the semicircular bending test, so in a different geometry. And here, the 3-point bending test. Looking at the result, we were able to see that the tensile strength is something that doesn't allow to have a clear differentiation of the different material. Or because we see that IDT, SIB, everything more or less, we are more or less the same result. Few megapascal of difference in the configuration. But the fracture energy is more consistent as a parameter constant for the material. So we can see that we are more or less with the same level for each material, and the difference among the different material is strongly consistent. So the result in terms of IDT, okay, allow that to say that are different, but are not so big. Like big is the difference between, in particular, the high modified bitumen and the natural one. So, looking the crack, this is just a collateral result that are the crack path measured, and this is just a representation. Here is the point where we calculate the fracture energy. You can see that even if the crack is not visible on the surface, the strain field is able to show that something is happening inside of the material. And we know that because we are looking at the same point when the crack is visible. So at the peak, in this case, is as the peak load, is at the peak of the stress and strain curve. So the process was exactly the opposite. We identified the point when the crack was visible, and the analysis we went back until the first change in the strain field was visible in the material. And this was the point that we selected as a first crack. So, in conclusion of this part, we can say that using a rigorous interpretation of the test condition, it's possible to measure tensile failure limit for different test configurations, and we were able to say that the fracture energy is a fundamental property of the HMA material. In particular, is the fracture energy calculated following the approach of the HMA Fracture Mechanics. That is one of the approaches that you can find in the literature. And the level of polymer modification does not affect the determination of the failure limits. Another step forward was to evaluate the role of the filler. For who is not familiar with the asphalt material, I can show generally if this is the grading curve. So the distribution of the aggregate in function of the size, when we are talking about filler, we are talking about this part. Traditionally, the definition of filler is below 0.075 millimeter. The name filler came from the fact that the idea was to use this fine particle to fill the voids in the mixture. But the research, the result in the research in the last 20 years showed that it was not only a physical behavior, but the fundamental interaction between the small particle and bitumen are able to make a lot of difference in the behavior of the material in function of the difference of the mineral characteristic of the filler. In fact, 10 years ago was introduced the definition of active filler in the side of the mineral filler, when instead of limestone and other mineral material, some people started to use fly ash, lime, cement, and different kinds, due to the fact that the interaction between this small particle, chemically and physical activity, with the fundamental component of the bitumen, make change in the aging process and in the change of the other property of the material. So the problem statement in this part of the research was that the cracking, together with other property, is a mastic-related distress. So the change in the mastics, or the change in the filler, we call mastics the combination between filler and bitumen, is something that can modify, strongly modify, the property of the material. In particular, we are looking the fracture energy and the tensile limit. So, in the literature, is clear from the work of several researchers that the effect of filler is based on a volumetric effect and a physico-chemical interaction between filler and the asphalt binder. So, what we are looking for was to define the mastic tensile failure limit with different combination of unmodified and polymer modified bitumen and different filler. And again, we used the digital image correlation to have more precise evaluation of the strain field in the material. And we applied this, we worked in both sides, in tensile failure limit in mastics and tensile failure limit in the mixture. To do that, we decided to move for a very simple test configuration in order to have a very simple characterization of the stress field. Starting the problem looking to the superpave drag tension test, but we had problem in that kind of test because the test setup was not sufficiently big to allow the application of the DIC. The stress distribution was not uniform in considering the shape of the material. The gauge length was absolutely not compatible with the DIC measurement, and the thickness of the specimen was too small to allow homogeneous results for the test. It was a test designed only to have a level of failure, just to measurement of force, not to understand what's happening in the material during the loading phase. So we changed the specimen shape mainly, considering the traditional dog bone was a combination of the superpave tensile test and the dog bone was something designed. In particular, we designed that shape in order to avoid as much as possible point of stress concentration. The only one was here, and we spent a lot of time making flat and not taking out any potential sharp point to avoiding any potential crack point of stress concentration, in order to have always the crack here. Because this is important, because with DIC we need an area clear where it's possible to point the camera and to collect the picture. And after several tries, we were able to identify that. Another important point was to define the load application, the stroke, because with a small velocity, we had too much creep, too much deformation in the material, and was not clear the area of the specimen to calculate the stress. But from the other side, increasing too much the speed, we had a very fast fracture and without any possibility to have a reasonable sequence of picture to do the back calculation. So after several trials, we identified 1.68 millimeter per second to do our test. And we defined the so-called area of interest in that area of the specimen, and this was the traditional one used in the DIC application on the indirect tensile test. Same setup. To analyze the problem was used a mixture with the same mixture used in the other part of the research, and 4 different binders with different combination of filler. We used limes, and this, I have to tell you, is an artificial series of filler, not filler always used. In particular, clay is not a traditional filler for material, but we use it to have something completely different from the mineralogical point of view. So the idea was to have limestone filler, absolutely mineral inactive filler, one active filler that is hydrated lime, and clay. So the idea was to have 4 completely different situations in terms of filler from the mineralogical point of view. Clay, I repeat, clay is something that you never find in the technology, but is an artificial way to do that. And at the electron microscope, we were able to see that already in the dispersion of the filler, something changed if we use filler based on limestone and filler based on clay. We are still not, I am honest, we are still not able to understand why this change happened, but something different appeared. So at the end we had 16 different mastics as 16 different mixtures. So the same mastic was applied in the mixture. So the first series of results was in terms of tensile strength, and we started to see that in terms of tensile strength we have some different, but we see that filler influence more the modified mixture. So where the polymer is, we have difference, but when we have no polymer, we have less difference in function of the different filler applied. And in terms of failure strain, we saw that filler influence modified mixture, and in terms of unmodified mixtures, in terms of modified mixture, we have contrasting results. We are not able to clearly identify a path in the behavior of the material. With the fracture energy, something is more clear, but again, difficult to find a clear path. The clear message is for sure the filler make a difference. So changing the filler, we have different behavior of the material. So it's something that is strongly related with the effect, the physicochemical effect that the filler has with the bitumen, because we are changing nothing in terms of the internal structure of the material. Even looking the creep compliance of the different mixture in function of the different combination of filler and blend, we have again different mechanical response. The most evident change is in the crack pattern in the different material. We can clearly see here in the IDT, so in the mixture, that when we have limestone and clay, we have different crack patterns that appear. I show one, but I tell you, believe me, we found similar behavior and similar difference in all the mixture. And adding an active filler, hydrated lime, to the same one, we have more difference in one case than in the other one. So the hydrated lime combined with clay has not the same effect in the crack pattern that the hydrated lime combined with the limestone. Here, another difference made by the different bitumen. Now we are looking in what's happening in the mastics. Here is the result on the test of the mastics, and we can see a more clear behavior. The clay mastics show, in general, a higher tensile strength than the other. It's something that was possible to see in the mastic and not in the mixture. The hydrated lime still has an unclear behavior. In terms of fracture energy, the unmodified mixture appear to have benefit by the presence of the hydrated lime. From the other side, the mixture with polymer modified bitumen appear negatively affected by the hydrated lime. So this is just an analysis of what's happened, but what is clear is that for sure the fracture energy and the tensile behavior of the material is strongly influenced by the filler. And again, if we go to look the crack pattern, we clearly see different behavior in function of the different mineralogical property of the filler and affected by the presence or not of the hydrated lime. Again, and this is something only on the mastics. One of the nice results of that research is that if we look at the same time the tensile strength on the mastic and the tensile strength calculated from the IDT, we have two completely different series of results. But looking together, the fracture energy calculated following the approach of the HMA Fracture Mechanics, we have a completely different picture. We found in several cases good agreement with the fracture energy calculated on the mastic and the fracture energy calculated on the mixture. The hypothesis, one of the hypotheses that we made is that probably the behavior is different in terms of stress peak and in terms of strain, but in terms of area below the stress and strain curve, so in terms of energy, probably we have good agreement that take the fracture energy to similar level. So, in conclusion, HMA cracking properties are affected by the filler nature. So the message sent to the people that design the mixture is that filler is not something that you have to buy on the market following the cheaper one, but is something that need to be considered due to the effect, that it has on the behavior. And the property, it seems more related to the damage accumulation, and in function of the nature of the asphalt binder. And again, we have the fact that the fracture energy density is a fundamental, it can be considered, is a very strong affirmation, let's say, can be considered a fundamental failure limit for both unmodified and polymer modified mixture and strictly related to the mastic behavior. Some consideration here on the fact that the nature of filler has a great influence on the mastic mixture damage distribution, and is something that we can synthesize that modified binder plus clay filler has a different strain localization. In one other case, we have large area. When we have modified binder and clay filler, we have large area of damage, something more distributed damage. Unmodified bitumen plus limestone has highly distributed damage, and modified binder plus limestone has more strain concentration around the fracture point. So, I hope to give you that my presentation enjoyed you and not too tired, and if you have any question, he will be very happy to answer.
Well, we have time for a few questions.
I'm puzzled by your term fracture energy, although in some places you do have this fracture energy density, because of course fracture energy is energy per area, and you seem to be calculating simply an energy density, right? So you have energy per volume. Can you comment?
Was the definition gave in the HMA was due to the fact that the integral was defined fracture density. Honestly, I was only taking what other people did, and I applied. I cannot be more precise because I really don't know exactly what is behind of this approach. I arrived in the research after. I am the experimental guy. Sorry for that, but I have my opinion, but it's on the work of other people, and I don't like to go too much in depth. And to
contact your former student, Professor Birgisson. Yes.
You showed a lot of pretty graphs, but you never said how many times, what sort of replication level are you looking at for your experiments? You had 16 different cases, but for example, on that plot, how many times were each of those replicated?
Generally 5.
So you're looking at, I can do this.
5 specimens for each one.
Yes.
You know, the idea was to have at least 3 consistent result, and the general was based at least on 5. 5 tests, taking the 3 closed. This was generally the replication of the...
But it would need, let's say on the order of 100 tests, if somebody wanted to replicate this with different combinations of materials.
Honestly, generally, I suggest not less than 3 for each material. We used 5. Some case more, in particular at the beginning, because we had not so much experience to say that this was noise and not some problem. So in some case here we arrived at 7 or 8 tests for each one. With the experience we were able to finalize at 5.
In the last slide, you mentioned that kind of you found that fracture energy is related to creep. But on the other hand, in all your experiments, very last conclusions. But on the other hand, in all your experiments, you had a constant rate of loading.
Where here?
No,
here.
Yes, related to damage to creep compliance. But basically, my question is, if having the same rate of loading, you are taking time-dependent effect out of picture. So you do not.
I understand you. I understand your point.
It's question number one. The second, kind of related, in concrete area, especially in Russia in 1970s, when people
nobody is perfect.
people related when people related damage to creep, they're talking about relating damage to nonlinear creep. The assumption is if your creep behavior is linear, there shouldn't be damage. As soon as you start in nonlinearity, that's like cracking, that causes the damage. So would you comment on this again?
I understand the point. The idea, okay, about the time dependence, yeah, I think that is a point that can be analyzed and discussed. In that case was an assumption that the application was a damage in terms that a dissipation of energy appear. So I can tell you, due to the fact that if we apply the constant application of load, lead the material to have damage. So in what way I can tell you is because we are saying that there is non-linear. The basic hypothesis is that if we apply something and we have some kind of dissipation of the energy that start and lead and take, in any case, do something in the material. So we have some damage. The concept is that this kind of damage is a damage that can be affected by healing. This is the difference. This is a damage that is not unhealable. So this is the things. Until we are probably the difference between linear and non-linear can be joined with the concept of the threshold. If we are below the threshold, this kind of damage can be healed. So if we have micro crack, if we are below, that can be sealed. This is probably something that we can combine. What you call linear and non-linear, we can, I don't know if I'm too much brave or something, but we can define that is below or beyond the threshold.
Following Joe's question, so when you define fracture energy density, I think this quantity will depend on specimen size. Because the strain curve will depend on specimen size. Large specimen got more post-peak, may even
the idea of the first fracture is to try to avoid the problem of the specimen size. So to find the first damage in the material is this is the concept, is to avoid the problem, because if we have a big specimen, of course the stress distribution is related to the specimen. The idea to take the idea is to analyze locally the material, so to consider the material locally and to have the first fracture and consider the material already damaged, even if the general specimen is still efficient, because we are not in the point of the peak of the stress and strain curve. So it is, in my opinion, if we reach the peak of the stress and strain, this is the failure of the specimen. When we take if we see, generally the first crack appears somewhere here. So if it's the curve. So when we have the first coalescence of when the micro crack appear, we have the first crack. This is the idea is to try to avoid the problem, is that to take the first.
But is this conventional definition of fracture energy? Fracture energy is the energy flux to a propagation of macro crack. It's not a micro crack.
Yeah. The problem is that the general energy. Please, can you repeat?
When you talk about the so-called first crack, I would say that if you start to look at the stress strain curves deviates from a linear part, to me that is a micro crack. If you calculate the energy based on that, basically you're measuring energy caused by the micro crack. The fracture energy we are talking about in fracture mechanics is mainly associated with the macro crack propagation.
Yeah, the concept is that if we go half of the threshold, you cannot go back, so you cannot heal. The material can, the crack can disappear. So you can have healing on that. If you are up, you cannot have healing. So this is something that changed, is the healing concept. Because if you have a material like steel or something, you have no healing. As soon you are over, it's done. This kind of material, due to the nature of the bitumen, you can heal. This is the difference of the fact. Because if you cannot heal, we are in the same page. But if you have a crack that can be healed, it's something that can go back, some kind of reversible, if it's possible to use the concept of reversible, because it's not reversible, it's the material that has a small level of damage, and the bitumen, the fluid nature of bitumen can come back and seal. It's not the crack that disappears, it's the crack that is closed. So if we go up, we make reach a level of damage that doesn't allow the nature of the bitumen to heal. This is the difference between microcrack and... Okay,
we have time for one more question.
I'm just still trying to figure out what this filler effects are. I mean, is it a particle size issue? Is it a chemistry issue? I mean, clay is not just clay. There's kaolinite. There's all kinds of clay. I mean, how do you characterize these fillers? Do you have particle size distributions? Did you take like one kind of chemistry and vary the particle size and particle size distribution, or take like the same size and vary the chemistry? Or I'm trying to like figure out what the heck is going on with this stuff.
Generally, what we did here is to change the physicochemical characteristic. One of the hypotheses is an unclear situation. We have different theory around at that moment. For example, in the case of the hydrated lime, one of the hypotheses behind the different behavior is that due to the high surface of the hydrated lime, the interaction between the oil that is in the, bitumen is traditionally considered composed by oil, asphaltene, and the 5 family. So the oil, that is the so-called volatile part of the material, that is the one that is the main act of the so-called aging. If you have bitumen, when the volatile part go out, you have a material that becomes more stiff, more brittle. A change in that behavior was observed, and the explanation was, the hypothesis was that the lime works as a sponge and attract the bitumen inside and make different and delay the volatilization of that. Another explanation is that the surface of the different material can be different and can interact in a different way with this heterogeneous material, having some kind of physicochemical reaction. Those are the hypotheses behind that. So it probably is. I think that is also an effect of the size, because we define filler below 0.075. But even there, we can have different size distribution. So probably is a size effect. Is the size, surface, and how much chemical physical active is. This is a combination of the interactions. The fact is that because the filler is very fine, the interaction is higher with the components of the bitumen. So we can have different change. It's a real change in the physical behavior.
Well, I think we don't have time for any more discussions. We can continue for wine and cheese reception, and let's thank Professor Tebaldi for his presentation.